During the last week, we've begun to talk about correlation and regression. So we've moved away from looking at differences in our average response variables between given groups to relationships between two continuous variables. By continuous, I mean either interval or ratio type data. On the screen is some data of the effect of different levels of fertilizer upon yield of grass. Producing a scatter plot of these on the right, you can see that as fertilizer increases, so does the yield. It's also important to note that in this case, our response variable, which can also be called the dependent variable, is yield, and our explanatory variable, or independent variable, is fertilizer. More specifically, it's thought that the level of fertilizer has an impact on the amount of yield. In the scatter plot, you'll see that our independent variable is plotted on the x-axis and our response variable is plotted on the y-axis. This is always the case. On our scatter plot, we can then draw a line of best fit through our data points. This is also called our regression line. Now, let's see how we'd run this data set through R. First, we check the normality of both the x and the y variables as shown here. I've used our old friend, the Shapiro-Wilks test, on both. In labs last week, you ran a more formal graphical method for testing normality. However, for a straightforward approach, we can look at these results. You'll see that both of the p-values listed are greater than 0.05, so we can say that the data is normally distributed. After you run a simple linear regression, the following output will be shown in R. You'll see there is firstly a repeat of the formula that we would have input. So that's a yield as a response, then fertilizer as the explanatory variable. Next is a 5-number summary, so you can see the minimum, the first quartile, the median, third quartile, and the maximum of the residuals for the regression. Following this is something called the coefficients, which we'll talk about soon. Finally, there's a section related to errors, R-squared, and F-statistics. It's these two sections in green that will be the key parts of the output for this class. Let's start with the bottom section, and in particular the part related to R-squared. You can see there is something called multiple R-squared and adjusted R-squared. These are two different variations of the R-squared that we discussed in class, which is also known as the coefficient of determination. Now, statisticians argue over which one should be reported. You don't need to worry about these fine-scale debates, but rather just know that the one we will be reporting in this class is the adjusted R-squared. In this case, it's a relatively high value of 0.9118. Now let's look at the other section, the coefficients. I've reformatted it slightly so you can see the different columns more clearly. It probably looks vaguely familiar, a bit like an ANOVA table. Importantly, you can see that there's obviously been two different tests that have been undertaken, as you can see a t-value and an associated p-value in the last two columns. When we are dealing with ANOVA, we know that such tests were directly related to the null hypotheses being tested. The same is the case for regression. However, we need to think for a second and make sure we know what are the null hypotheses being tested in simple linear regression. We're looking at relationships, right? If we think back to our scatter plot, we're looking for a change in our response that occurs as a result of a change in our explanatory variable. If the explanatory variable did not have any impact on the response, there would be no clear trend in the pattern of the response. Instead, we would see random values of yield regardless of the level of fertilizer. If this was the case, i.e. that we had random values, the line of best fit would just become a flat line. A flat line has a slope of 0. So, One of the key things we're testing in regression is whether our slope is significantly different than 0. Our null or our dull hypothesis is therefore that there is no relationship between the response and the explanatory variables. Or, putting it another way, that the slope of the line of best fit is 0. Now let's look at the values that R has estimated. The value listed next to the explanatory variable is actually an estimate of the slope of the line. Next is the standard error of the slope. Then a t-value. Actually, it's a calculated t-statistic to determine whether the estimated slope is significantly different than 0. And finally, there is a p-value for this statistical test. The top line of the R output refers to something else that we're testing in regression, whether our line goes through the origin or not. More specifically, we're testing whether the intercept equals 0. The first value here is the estimate of the intercept, the standard error of the intercept, the t-statistic calculated to test whether the intercept is significantly different than 0, and finally the p-value for this t-test. Here's a few questions to make sure you understand what is being presented by R. Question 1. Is there a relationship between fertilizer and yield? In other words, is there a significant slope? Question 2. Does the line of best fit go through the origin? Or in other words, does the intercept equal 0? And question 3. What is the equation of the line, also known as the regression equation? I'll give you a minute to think about it.
ni pakiakia, tau mole mole haufelia, aunuitaani na sema batani.
Okay, question 1. If we're being asked whether there is a relationship between the response and the yield, we're actually being asked if the slope of the regression line is different than 0. This hypothesis is tested by the second line of data. The estimate of the slope is 0.81139, and the p-value for the test is very, very small. So, based on these results, we can say that there is a significant positive relationship between level of fertilizer and yield of grass. Before moving on to the next question, I also want to note that the estimate of the slope that is listed is a quantity called B in our regression equation. Question 2. We're now being asked whether the line goes through the origin, or in other words, whether the intercept equals 0 or not. So in this case, we look at this first line of output, and we can see an estimate of the intercept is 51.53, and there's a p-value of 0.00394 for the t-test of whether this value is significantly different than 0. Due to the low p-value, we can reject the null hypothesis and instead say that the intercept is significantly different than 0. So in other words, it does not go through the origin. Also note that the estimate for the intercept is the quantity A in the regression equation. Last question, regression equation. Well, we know the regression equation is y equals bx plus a. Now that we know what a and b are, we just plug them in to give us the equation as shown. Alright, I hope this helps bring some insight into regression. Let me know if you have any questions. Good luck.